All right, so we're going to look at another example about continuity and discontinuities for a function. Here we have a piecewise function and a question, where is this function discontinuous? So that's just kind of the flip side of asking a question about where is this function continuous. So we want to pay attention to how the question's asked to make sure that you're answering what's actually asked. But we're going to think about the problem in essentially the same way. I'm going to start looking for places where this function might fail to be continuous. It would be where one of these three conditions fails. This comes from the definition of continuity here. This is the definition of what it means for a function to be continuous at x equals c, which you can break down into kind of these three categories. This first one is really about domain. The second one would be about limits, any place where you might have some interesting limits to consider about the function. And then the third one, you'd want to make sure that those things are equal to each other. Okay, so when I look at this function and I'm asked to think about where this function might fail to be continuous, the first thing I would start to think about with this function is domain. So this has a lot of stuff going on with it with domain. I have three different function equations making up the three different pieces for this piecewise function. And then I also have some domain restrictions that are part of the piecewise function definition here. So one thing I might notice, first of all, is that in these intervals that are given, there are no x values that are left out in those intervals. I've got x less than or equal to 0, and then x between 0 and 4, not including 0, but 0 is included in the first piece. X between 0 and 4, not including 0, yes, including 4, and then x bigger than 4. So between those intervals, we've covered all real numbers. So if I have any domain restrictions, those are going to come from the function equations that I have over here. So when I start by thinking about where this function is discontinuous, I'm going to start by thinking about where the function might fail to exist, which is really about the domain. Okay, so I'm going to kind of break this down into the three different pieces here and think about those for a little bit. All right, so for the tangent x function, we basically have four reasons when you're thinking about an equation that you might have domain restrictions. One of them is about denominators. And this has a kind of hidden denominator in here. If you really remember what the definition of tangent of x is, that is sine of x over cosine of x. And so we're going to run into some trouble anytime that denominator is 0. So we want to think about all of the times where this denominator would be 0, all the times where the cosine function is 0. So this is where it's helpful to have a fluent understanding of the unit circle, be able to think about all of the inputs for which the cosine value is 0. So when I think about the unit circle, I'm thinking about here and here on the unit circle. So there's really infinitely many values of x, all the different times I might go around the unit circle, forwards and backwards, all those times I hit those two places on that unit circle. So there's really infinitely many values of x for which this function is undefined. Those are the odd multiples of pi over 2. Just in kind of one revolution around the unit circle, might say pi over 2 and 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Also the negatives. So this is going to be undefined when x is plus or minus, I'll just list some of them out here, pi over 2, 3 pi over 2. You can write this as a formula using maybe a k pi, but we'll just kind of make a list here. Okay, not all of those are in the interval, though, for which we're using the tangent function for this piecewise function. So the tangent function is only using x values that are less than or equal to 0. So really just all of the negative x values here. So that function is undefined at all of these negative odd multiples of pi over 2 that are in that interval. So we're going to have some discontinuities. Let me write them over here. When x is equal to negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc. And you can write that using negative pi over 2 plus k pi, where k is a negative integer or something like that. But these are all the places where the function is going to fail to be continuous because of the tangent function being undefined. All right, for the second piece of the piecewise function, y equals x over 2, I do have a denominator, but that denominator is never 0. So I don't run into any domain restrictions from that part of the piecewise function. For the third part of the piecewise function, the denominator is in factored form, and it might be tempting to cross out those x minus 5s. But remember, that actually changes the domain, and it's not the same function when you do that. So when I think about the domain, I need to pay attention to this version of it. All right, so this part of the piecewise function, this is undefined when x is equal to 5 or x is equal to 6. And so to see if those are part of what I'm going to list here for my discontinuities, I need to pay attention to the interval that we're using for that piecewise function. It says x is greater than 4. We're using that piece when x is bigger than 4. And these values are both in that interval. So I'm going to have some discontinuities also at x equals 5 and x equals 6. OK, so all of those discontinuities, all these odd multiples of pi over 2, negative odd multiples of pi over 2, and 5 and 6 are discontinuities, places where this function is discontinuous for this reason. The function is undefined at all of those points. At some of those points, the limit may also not exist, but what I'm going to look for here is any additional points that are not already in my list where that limit might fail to exist. So if you think about substitution shortcut theorems that we have for evaluating limits, really the places besides domain where we might have limits that fail to exist would be where we might have pieces of a piecewise function that may not meet at the two pieces. So besides the domain restrictions that perhaps also require that the limit does not exist because you can't find that limit, the additional pieces, though, that you're going to get for discontinuities would be where pieces of a piecewise function fail to meet up. So that could happen at the places where I have the break here. So in considering the second part here, and thinking about where we might have discontinuities because of the limit, or the limit not equaling the function output, I'm really going to have to look at those pieces on that piecewise defined function and see if those pieces meet up. So I need to think about the limit as x approaches 0 of our function. And because I have two different functions, function equations on either side of x equals 0, I really need to look at those one-sided limits and see if they agree. And if they do, then this is my limit. I guess we have our function called g of x. Let me write this g of x there. All right, so we're going to look at the limit as x approaches 0 of g of x. And we're going to do that from the two one-sided limits. So the limit as x approaches 0 from the left of g of x. On the left side, we're using the tangent function. Okay, x equals 0 is in the domain of the tangent function, so we can use a substitution shortcut theorem for transcendental functions to get that this limit is tangent of 0, which is 0. And then I need to consider the limit as x approaches 0 from the right. And so when we're on the right side of x equals 0, we're using this function, x over 2. And so considering that limit, we have a polynomial function. So I can use a substitution shortcut theorem for that, and I get 0. Those two one-sided limits agree and are 0. So this limit is also 0. OK, so one of the places I was considering that I might possibly have a discontinuity would be at 0 if the two pieces of that piecewise function don't meet up. And that would happen if the limit doesn't exist or the limit exists but does not match the function output value. OK, so here I have the limit for the g of x function. I might think about what is the function output value at x equals 0. And so paying attention to my inequalities, when x equals 0, the output is tangent of 0, which is 0. So the limit exists, and the function output is 0, and they agree. So we're OK at x equals 0. At x equals 4, you might think about the limit as x approaches 4 for this function. again, because the piecewise function breaks at x equals 4, I really need to consider each side of x equals 4. So a limit as x approaches 4 from the left of the function. When we're on the left side of 4, we're using the function equation, f of x equals x over 2. Substitution shortcut theorem for a polynomial, we get 4 over 2, which is 2. And when we're on the right side of x equals 4, we let x approach 4 from the right, we're on the other piece of the piecewise function, x minus 5 over x minus 5 times x minus 6. We can use a substitution shortcut theorem for rational functions. Since 4 does not make the denominator 0, we can use that substitution shortcut theorem. So we'll have 4 minus 5, which is negative 1, over 4 minus 5, which is negative 1, times 4 minus 6, which is negative 2. And so for that limit, it looks like we get negative 1/2. Okay, so the two one-sided limits do not agree, which means the two pieces of that piecewise function don't meet up. And so this limit here does not exist. All right, so in addition to my list of points that I have here that are really about domain and why this function might fail to be continuous because of the first condition, I have one more to add to that list. This work here shows that we also have a discontinuity at x equals 4. It's another place where this function fails to be continuous, another discontinuity, for the reason that the limit does not exist. Now, some of these other ones that we talked about at the beginning, some of them the limit may exist or may not, but I don't really need to check that unless I want to classify those discontinuities as removable or non-removable. If any one of these conditions are violated, then we have a discontinuity at that point. Every place else, since I have substitution shortcut theorems that tell me that at many points I can just substitute in, if without the domain restrictions and the pieces of the piecewise functions, as long as those two conditions are met, if I have both of those things, they will be equal for this one because of those substitution shortcut theorems we had. So in general, on a piecewise function, when you're looking at why a function might fail to be discontinuous, you're really looking for these issues here: domain and pieces of the piecewise function not matching up. And so you need to just consider the one-sided limits and see if they agree. If they do agree, you can also check to make sure that the function output agrees with that as well, like we did here. All right, so that's, if you can handle discontinuities with a problem like this, you can probably handle any problem that's going to be thrown at you. Make sure you can handle also if there's logarithms or exponential functions, but there's a lot going on with a problem like this, a lot to keep track of. So these would be all the places where we decided this function is discontinuous.